I'm curious, like, it sounds like you mentioned that you had worked with Pei's NAR system, or at least the logic part of it to start with.
Yeah, not his current NAR's implementation, but the
Okay.
NAR's logic in a different implementation.
Okay. And is that why you deviated away from his overall design?
No, I mean, well, that's a big question, actually. I mean, so in the dark ages, like way back before there were computers, well, not that long, but Pei and I actually worked together in a company that I co-founded in the late '90s. So in that system, the WebMind AI system, which was architected a bit differently than OpenCog, NARS was the logic engine of that system. So I work with NARS a bunch in that context. And then WebMind was more of a heterogeneous architecture where you had a whole bunch of different agents working together on the same knowledge base of nodes and links. And I didn't think as hard about the interactions between the different components. It was more, it wasn't a blackboard architecture, it was a little more like that. It was a little more like I was just thinking we would throw together all these different agents, and as long as they were all smart and building on the same knowledge base, they would make us something smarter and smarter. And as one of the many things I learned through that experiment was that it's really hard to get all these different systems to cooperate together in a meaningful way. And just working out the semantics is hard. So when two agents act on the same node or link in the knowledge repository, it doesn't mean the same thing to the different agents. Like, you remember those discussions about procedural knowledge, where we had Anton Kolonen's system for learning procedures and your system for logic, and trying to get declarative and procedural knowledge to work together on the same nodes and links so they each meant the same thing when they were acting on the same nodes and links. Those discussions seemed to go on for months, and we finally came up with something that made sense, I think, but it was so complicated. And so when I started, that company went defunct for unrelated reasons due to the business that it was trying to do in the .com era. And then when I started over, trying to design a new AI system in 2001, 2002, which was the Novamente cognition engine, the predecessor to OpenCog, I started thinking really hard about, how do we reduce the number of cognitive agents to the minimum possible, and how do we make them work together more simply, so that dealing with the integration of them all doesn't lead to such complexity as we were seeing in the WebMind design. And as part of that, it really kept seeming like it would be nice to have an uncertain logic that was probability theory based. I don't really buy the arguments that probability theory is the only correct way to do reasoning for an AGI system. I mean, the arguments from, say, Cox's axioms or De Finetti's Dutch book arguments, these arguments are fairly strong. I mean, they're math, right? That if you're going to do reasoning in a way that obeys these certain rules, probability theory is the way to do it. On the other hand, no system with finite resources could ever do reasoning according to those axioms, which kind of weakens the argument. So I don't buy that probability theory is the only way to do intelligent reasoning. However, unlike Pei, I see no reason to believe that probability theory is an inadequate way. I think probability theory is one among the many workable ways to do uncertain reasoning. And in practice, you need to accompany probability theory with certain heuristics anyway to make it work under finite resources. So I'm not saying that NARS wouldn't work. Actually, I don't know if NARS would work or not. But I decided I wanted to have something probabilistic because there were many other components of the system that I wanted to use that were probabilistic. And then using a probabilistic logic engine would just make that easier. So for example, we do automated program learning, which I do feel is a very powerful way to learn procedures. We do that using Moses, which is like genetic programming, but with probabilistic modeling of the population of programs. Now, since I was doing procedure learning using Moses, which is probability theory based, it's very convenient to have probability in your logic. Now, another approach, of course, as Pei is doing, is to do procedure learning in a way that is compatible with NARS. And I'm not saying that couldn't work either, but that seemed harder to me. I guess I like probability theory more than Pei does in AGI context. So this comes down to more of the consilience or compatibility among the different parts. Like the way I was thinking when I was doing WebMind, it was all right to have a probabilistic-based, say, procedure learning approach and a NARS-based logic approach, and kind of make them all work together in the same knowledge network. And that is mathematically possible. It's semantically possible, but it's really, really complex because you constantly have to deal with semantic and mathematical translation between the different representational idioms of these different systems. So by using probability in the logic and probability in all these other things, it means that my forthcoming book is only 900 pages instead of 9,000 pages, which it's already really complex, even trying as hard as I could to make it simple and use the same language and representations in the different parts. But the complexity, I really think, is a feature rather than a bug, because if you ever study neuroscience, like a graduate level neuroscience textbook is like that thick, right? But yet, each chapter is only an abstract of what's known about that part of the brain. Like, you look at the 1,200 to 1,500 page neuroscience textbook, right? Then the chapter on the anterior cingulate cortex is 15 pages. But yet, it's just a pointer into the literature on the anterior cingulate cortex. I mean, the brain is just amazingly complex, and OpenCog is nowhere near that complex. Even WebMind wasn't nearly that complex. So I think there's no rational reason to believe that a human-level AGI is going to be a simple and elegant thing where there's one core architecture, one algorithm that does everything. I mean, with all due respect to Pei. I mean, it may be possible to do it that way, but the one working example we have is astoundingly and hideously complicated. So, I mean, compared to the complexity of the brain, NARS and OpenCog are basically equally simple, even though OpenCog is 10 times more complicated.
The argument, of course, well, I'm not going to take sides, I'm just throwing this out here. The argument could be made and would be made probably by a significant portion of the AI community that books on bird flight will become very, very thick if they start talking about feathers and the chemistry and the skin and heat, how the bird keeps itself warm, etc. And that analogy is perfectly mappable onto AI, where flight is the intelligence and brain science is the bird feathers, etc.
Yeah, that analogy is an interesting one. I mean, on the one hand, I would want to observe that there is a sense in which bird flight is more generally capable than airplane flight. I mean, airplanes are narrow flying machines. They do fly faster than birds. On the other hand, birds can, if you vary the conditions, birds can adapt to them much, much, much better. So in a certain sense, although I've used that argument as well, to say, well, in a different way, I've used that analogy to say, well, people said flight was impossible, but now look, we can do it. We didn't need to model birds after all. But actually, birds have a lot more adaptability and generality than airplanes or helicopters or whatever. But the other part of that argument that doesn't quite hold up is, if you look at a modern airplane, it's really complicated. I mean, there's a lot of different parts in there that do different things, and they're all engineered to work together over a long period of time. I mean, there are, in a sense, simple principles of flight coming out of the Navier-Stokes equation and fluid dynamics and so forth. But if you look at all the parts inside a modern jet, there's many principles involving the many different parts there, and they all work together, and they were...
And most of those have to do with carrying passengers, and birds don't carry passengers.
Well, no, I think a guided missile also, which doesn't carry any passenger except some explosives. There are thousands of different electronic parts inside a modern guided missile that all work together well. I mean, the Wright brothers plane was pretty simple, but that was a much more narrow flying device, right? It was very hard to get that to do anything. So, I mean, I think if you put those two things together, the fact that birds actually are more general flyers, and the fact that modern flying machines gain the generality they have above the Wright brothers through greater complexity, you don't really have an argument that there's not one really simple flying machine with like one moving part that flies with the same generality as a bird, right? I really think computer scientists just like to think in terms of simple, crisp algorithms, so that they would like to think that you could make an AGI that way, because that's what they know how to do, right? I don't think that computer scientists have some philosophical or principled argument why human-level intelligence should be achieved by some one simple algorithm. I've never seen that argument. It seems more of a pragmatic belief based on either wishful thinking or based on the intuition, like, wow, this simple algorithm could play chess or could drive this car. Why can't it do all this other stuff? Right? Yeah, perhaps.
That AI people and computer scientists in general wants to be as elegant as physics, and so they always try to look for the golden.
Yeah, but the problem is physics isn't as elegant as physics either. I mean, if you look at like condensed matter physics or the physics that is done to make real stuff operate with physics, it's also pretty complicated. I mean, it's only, there's a few core equations in elementary particle physics, but physics doesn't actually derive the operation of a telephone or something from those core equations of particle physics. No one can even derive the periodic table of chemistry from the bottom up yet, without using a lot of parameter setting gotten from chemistry. So I mean, even physicists have physics envy, right?
Maybe it is possible to come up with an argument that supports that it goes beyond physics envy. Our whole genome fits on a CD-ROM. And of that, only a very, very tiny fraction is going to encode the principles that organize the structure of our brain, that define the structure of our brain. And this means that if the whole of our body has a complexity that is significantly below the current edition of Microsoft Windows, and only a small portion of that is dedicated to defining how our brain works, then in some particular sense, it's not that complicated. In another sense, it might be extremely complicated because we know that the definition of the Mandelbrot fractal is like this, and it is of stunning complexity, not computational complexity, but in complexity of its appearance and the structures that we can discover in it. And yet, for instance, a new study of the NIH suggests that the brain is actually not that complicated in its makeup. And it seems that we only have a few major architectural principles that define an overall layout of the brain, and we have maybe a few hundred organizational principles for local learning, for organization of the columns and so on, that define the microstructure of the brain. And this is not the topic we are working at. Rather, we are looking at macroscopic functionality. We are trying to define the spirals of the Mandelbrot fractal. And we could argue that this is not the best way to go to describe the Mandelbrot fractal, even though it's the most intuitive one. We discover over there is this little seahorse-like structure, there's this tail, and there is this copy of this one, and so on and so on. Maybe we should be looking for something that is orthogonal to that. Maybe we should be not adding functionality in our systems, taking reasoning and taking representation and taking perception and taking motivation and putting all these things together in a more and more complicated machine, and then we add a module for stereoscopic vision and another module for tactile perception and so on and so on and so on. But rather we should be looking maybe at an extremely complex system, like a very highly connected recurrent network, and then try to look for the right set of constraints, add just those constraints that are necessary to make it behave the way we want it to if we connect it to an environment. Now, I wouldn't say that I am completely betting on that argument. I just do think that it's a completely valid argument that could be put in against our current approaches, which are basically all constructive instead of restrictive.
Yeah, well, I think the first argument you made about the genome it's interesting, but I think that's too weak to disambiguate between any existing AGI approach. Because say OpenCog is big and complicated because it's C++ code, but if you re-implemented OpenCog in Haskell and then zipped it, you would get something small enough to fit in a fraction of the human genome. So I mean, and I think the same is probably true with any existing cognitive architecture. So I think none of us right now are doing anything that's too complicated to be jammed into the genome. I mean, the Mandelbrot set, sure, that's like Z squared plus C is really small, right? But OpenCog or micropsi or SOR or whatever, if you coded it for compactness, could be jammed into 10% of the human DNA or something. So, I mean, that argument rules out insanely complex software systems, but it doesn't seem to rule out the sorts of things people are actually looking at if you take that literally. I mean, the other approach you described seems in principle feasible to me, but one argument against it in practice, which I'm sure you're well aware of, is it's in essence what you're doing there is what evolution did, right? Rather than what development did. I mean, what evolution did, in essence, going from the prebiotic soup up until now, is it took a bunch of entities connected to each other with the ability to interconnect and interadapt and construct new things from each other. And through selective pressure from the environment, evolution eventually created organisms and intelligence and so forth. And that's not what happens in the human infant, as the human infant's mind develops, of course. There is a code that's written there, and it's fairly precisely configured so that certain functionalities come into the infant's brain at a certain point in time based on the development that's already happened and so forth. So it's a system where some of the code comes out in the beginning, then some development happens, some more code manifests itself, then some development happens, some more code manifests itself, then some development happens. I mean, it's pretty far from just a heterogeneous, a self-organizing network that is constrained by the environment and then grows into a mind. So, I mean, I think it could be interesting to try to make something that doesn't have pre-wired functionalities of any kind, but there's have to be something in between what we're doing now and just a kind of recurrent neural net that self-organizes into intelligence.
Ben, it's much worse than that. I know that OpenCog is already 90% of the way, and now you can look at the next 90%. My own architecture is maybe it's 2%, maybe it's 5% of the functionality, and I'm probably being too optimistic here. And so I do think that if I continue with the method that I chose right now, maybe this is the most tractable way of tackling the problem, but it's one that is going to end up in complexity. And I'm not saying that we should go any other way, but there's still a possibility that what we are looking for in the end, with hindsight, is much simpler than the thing which we are constructing now. And I'm not just trying to do what evolution did, I'm also trying to do what development does. And in another respect, I try to overcome or bypass what evolution did. If you look at the theory of flight, it's probably very easy to write this down on half a page. And yet, it is not very difficult to write a very meaningful book of 9,000 pages about the intricacies of flight and flying and how to understand flying and flying organisms and the development.
Build an airplane is not half a page.
It depends. I mean, if you look at the first airplanes, it's not that difficult. General principles of aerodynamics or a general sketch on where to put the wings and the engine. No, I don't think it's that difficult.
From an engineering perspective, if we agree, and I'm not sure if we do, but say we agree that the target complexity of the behaviors we ascribe to an AGI is so daunting that it's impossible for human programmers to build it all at once. So we must at some point delegate to the system itself some of what sort of abilities to construct itself. Therefore, the system must have a representation of itself. Therefore, this representation must be smaller than the system itself. I mean by that, the system must be compressible. And compression demands, to some extent, some regularities. So I don't really understand what are the engineering principles that you use when you add a component here, you choose to remove this one and add another one instead. How do you really engineer your own system, actually?
I didn't quite understand the connection between the two halves of that question. I mean, you start out by pointing out that a system, to have human-like general intelligence, has to be able to learn, and in order to learn in a sufficiently general and flexible way, it has to have a representation of itself. And that's true, and I think that representation is learned itself through experience. I mean, when a baby is born, it doesn't have a representation of itself. And then through interacting with the environment and seeing how the environment reacts to it, and how its body reacts to the environment, through all these interactions, it builds an approximate self-model. Not an exact model of itself. Of course, all of our self-models are largely fictional, but they help guide what we do. So I think the self-model has to be learned. That's the first half of your question.
That's okay with me, but I'm not.
But then the second half, you asked how, in OpenCog, how we decide which parts to add to the system?
Yes, the first part of the question was related to unified cognitive architectures versus integrated, just like yours. And I was trying to argue that some sort of regularity is necessary if one pursues the idea of a system that bootstrapped and construct itself over time to reach the desired level.
Well, I think that in the human example, there are limits to the degree to which we construct ourselves.
I'm not talking about the humans at all. I am talking about some key fundamental engineering principles to build a machine. And I know that the humans, they don't change their arms every day, of course not. But
well, we also have a limited capability to revise our own cognitive and perceptual processes too. I mean, we do have some ability to self-program and self-modify, but it is limited. I mean, AGIs don't have to be limited in that way, but we certainly are, and that shows that a system with a fairly limited capability for self-reprogramming can have human-level intelligence, because humans do. But I feel I'm still not getting the crux of what's your question.
So that drives me to the second part, on which engineering principle do you guide the construction of OpenCog?
Well, engineering principle, I wouldn't put it that way. I mean, I would say the overall architecture of OpenCog is guided by cognitive science and cognitive psychology. So it's basically guided by what do we know that the human mind does? What kinds of representations do we know that it has? What kind of learning do we know that it does? What kind of pattern recognition do we know that it does? Look at everything that the human mind is known to do by cognitive science and cognitive psychology, and then that's sort of the requirements list. But that uses apparently scalable representations and algorithms from computer science, and I don't know that I would call those engineering principles. So, I mean, then there's the whole software engineering side, which is based on engineering principles, but it is probably orthogonal to what you're asking about.
So in OpenCog, have you given any thought to real-time processing? And if not, do you expect to have some problems with all the large number of different heterogeneous processes, because all of these presumably operate at different frequencies?
Well, we're doing real-time processes in the virtual world context now. So I mean, it controls an agent that acts in the Unity 3D world. It gets perceptions from there. It sends actions back. And basically there's a cognitive cycle which circles around within maybe half a second at the moment. It could be done faster depending on the hardware. That goes through everything that's needed to perceive what's in the world, decide what needs to be done to achieve its goals and issues in action. And then there may be other processes running in other threads in the background that are interacting with the same atom space, but the cognitive cycle is sort of the main loop that is run through all the time that interacts with the world. Now, dealing with a robot with the perceptual data, that's much higher bandwidth, right? And I think we can deal with the same architecture, but then the way we're trying to handle that now is to use a separate perceptual processing front end, basically, so that, say, the destined hierarchy does vision processing. That's implemented in CUDA. It runs on a bunch of GPUs. So that's pretty fast. And then in routine cases of visual or auditory perception, Destin will just recognize what's there and feed that information into the atom space where it's handled by the cognitive cycle, just as if something was coming from the virtual world. Now, in a more difficult case of perception, you have feedback coming from cognition to the perception hierarchy to guide its own recognition. Then it's going to take longer. But that's just like if I'm squinting at a scene in the dark, it's harder for me to make out what I'm seeing. And there's what you find is feed-forward networks, generally speaking, can model what human beings do visually if they're given less than half a second or something to perceive. So if you give people a bunch of pictures, rapid fire, say, what's that, what's that, what's that, what's that, what's that? They're not correct that often. They can make simple perceptual judgments. The pattern of errors they show is similar to the pattern you get from, say, Tommaso Poggio's feed-forward neural net. Whereas when humans take less than half a second or so to process perceptual data, that seems to require feedback from cognition to perception. That seems to be slower. And that's going to be the same way in OpenCog or anything else. So I think that, yeah, right now, if you make good use of technologies available, I mean, you use multiprocessor machines and use good concurrent processing techniques, use GPUs for vision and audition processing. If you use all these technologies, you seem to be able to do real-time processing in simple robots or in game characters and so forth. And of course, the hardware is getting better and better. So I think 10 years ago, I think it was a lot worse. You could do it, but you'd need really expensive, specialized hardware. And now you have to use technologies that are a pain in the ass, but it's doable using relatively inexpensive hardware technology.
Even more important than speed, do you spend some, none, a lot time on getting your components in your architecture to be anytime, so that they can, improve their output linearly over time, so you can actually get the results, the best possible result at the time you need it, even though they may not be perfect?
So that's the goal, is for every component to be like that. And often the initial version of some component of the system runs in more of a batch mode, just because it's easier to program that way. And then it is revised or re-implemented to be anytime. So the probabilistic reason engine and attention allocation are anytime. The Moses machine learning algorithm is fast enough that we can operate it that way, even though internally, at the finest grain, it isn't that way. But some of the other more recent components are not yet. Like the system we use for pattern mining of the atom space, just generically scan through the atom space and find frequent or surprising patterns in the atom space, or to mine the Destin hierarchy for patterns. Right now, that is not any time, but it should be. But that's because that's new. So, yeah. So the basic answer is we always do that, but it's always extra work, because the easiest way to program it is never that way.
Danny?
So
And I'm fairly new to the AGI environment, really. The AGI conference last year is my first kind of dive into it. From a methodological perspective, I guess or how to bring about methodology, one of the thoughts that occurs to me is that it would be nice to have a particular well-defined challenge, and albeit this would fit into that category of a very specialized, AGI focus. But and there may well existed, or I think had such a thing, such a challenge to take place. First of all, has that occurred? Has there been
It hasn't occurred, and we discussed this kind of endlessly in this 2009 AGI roadmap workshop that I mentioned in my talk. And I mean, I've talked to Peter Diamandis about doing an AGI X Prize of some sort. I mean, after a great amount of thought and study, I decided that's a dead-end line of thought that should be abandoned. And I mean, if you want something that can end up with AGI at the human level, and you can proceed along some incremental path toward human level AGI, and at each step, you can rigorously evaluate how far you are along the path in a way that can't be gamed or cheated somehow by someone hacking something for that special application. I came to the conclusion that's impossible. Now, maybe that's pessimistic and it's possible, but you can run down so many different possibilities, and once you've specified a task really precisely to be, say, a quarter or a third of the way toward human level AGI, it seems to come out there's some way to approach it using narrow methods. So take, for example, take Wozniak's coffee test, right? Now, I'm willing to believe that the only way to really do that is to have something like a human level AGI, to be able to go into a random American house and make coffee. On the other hand, let's say you try to specialize that. So let's go into a certain percentage of houses with certain restrictions and make coffee, right? It seems like either it's become so hard that it's just like the original thing and is equivalent to making a full-on human level AGI, or it is specialized and you can then just feed it with a description of 1,000 kinds of coffee maker and the layout of many types of house and cupboards and so forth, and just hack something to do just that. And take another example of playing an arbitrary video game, right? In principle, that requires, I'm willing to believe, a human level AGI. On the other hand, once you start restricting it, you could make a system and you could train it on 10 major genres of video games, right? And teach it many different specific video games so that when you gave it a video game, it would do pretty well. Now, what I would submit is that on these specific tests, the proto-AGI system is going to do worse than a system built by paying the same amount of money into hacking it and teaching it a whole bunch of video games or how to make coffee in a whole bunch of different houses. And I mean, this is something Joshua and I didn't quite agree with at that workshop. Is he felt that something like story or scene understanding might be able to bypass that, when a proto-AGI system would do better at summarizing and answering questions about a snippet of a movie than a system that was kind of jury-rigged and hacked to be able to answer questions about movies. And so it's not clear. It's possible that you could do something like that. But my own feeling after a lot of thought was that pretty much any test you come up with to measure, are you 25% of the way there, that test is going to be hacked by someone who has just put a lot of effort into doing well on that test. And the fundamental reason I think for that is that AGI, and this reasoning comes down to my own philosophy of how to make AGI work. I mean, if AGI relies on getting a bunch of different components to work together in a way that's fairly sensitive to their tuning and their interoperation. So let's say AGI required 10 things to work together well. And if you had only 8 of them there, it sucks. But if you have all 10 of them there, it's really good, right? Then anything that's halfway there, in the sense of having only 5 of the components really working well together, is going to suck and may work worse than some narrow AI kind of jury-rigged thing. Only once you're really, really close to the end goal are you going to have something that's good enough to outperform narrow AI solutions. And that's pretty much the way that I think it is. So I mean, it would be nice if you had that sort of test for incremental progress, but I don't think it's there. No, I do think you could test the end goal. I mean, I like, say, the robot college student test appeals to me. Like if you can make a robot that could go to Reykjavik University and pass all the classes, and walk around like all the students can, talk to the professors, get the test on a piece of paper, write down the test answers with a pen, figure out how to use the computer lab. I mean, if you had a robot that could get a bachelor's degree from this university without any special allowances, even if that robot didn't look like a human, and even if it looked dorky like a robot and came across as socially awkward, it wouldn't have to fool people into thinking it's human, I would be willing to say, yeah, that guy has human-level general intelligence. I mean, there's classes in a lot of different topics. The curriculum changes each year. The professor may throw some random thing at you. I mean, that's not infinitely general, but neither are human beings. So I think you could measure human-level intelligence in a qualitatively plausible way that's better than the Turing test, that doesn't require fooling anyone to think that you're human. But that's not necessarily good at incremental. It's not necessarily good at measuring incremental progress.
The response concerns me most about is that if you look at a recursive incremental sort of technique or testing method, if it's not possible to find the first increment of that, then it's not possible to find the last one, and therefore this whole sort of direction would seem to be ill-founded from a scientific perspective. So I don't think that's true. I think that we can define something. Like
What's your example? What's your suggestion?
Well, hopefully, in a first instance, there is a challenge that one could lay out that prescribes at least certain aspects of general intelligence that I would agree, could not eliminate all the.
Well, I understand the general idea, but do you have a specific challenge problem in mind?
No, I don't. No, not at all.
Okay, well,
I was first asking whether what.
No, I mean, it's a very appealing idea. My prediction is the further you go down that route, the more you'll see how problematic it is. I understand the appeal of the idea.
But what you're suggesting is that you'll never be able to test for it.
No, I think you can test for whether you have human-level AGI. I think it's very hard to make a test of partial progress, which will distinguish things that are genuinely partial progress toward human-level AGI versus things that are narrow AI dead ends. I think that's what's hard.
So you can test at the end, but not the n-1 iteration.
Maybe n-1, but so what? If you can't test that you're halfway there or a quarter way there, it's not much use as an incremental test.
Yeah, I probably haven't thought nearly as much about it as you have.
The thing with the college test is that, which worries me about that it, if you take a random sample of the human population of that planet and apply that test to them, then a lot of them might fail it because they don't have the necessary the individual developmental trajectory that would enable them to perform well at that test. Yeah. So I rather prefer something that doesn't induce you as an experimenter to do the second step before the first, because you might be better with a system that Loebner Prize style specifically addresses the challenges that come with the college thing instead of addressing the challenges that come with AGI. And I think that, for instance, scene comprehension, I only took the movie example because this gives you scenes that are reliably repeatable across systems and situations, so you can have a competition. And narrative comprehension are tasks that I think that require a large degree of AGI, not all the components, but for instance, I think that motivation is missing there to some degree, but I don't think that motivation is that difficult, as we hopefully will see tomorrow. And on the other hand, you do not have to put in additional functionality, which would be the second step after the first one. It's something that a toddler can do, and where you can see progress in different toddlers depending on their mental age, and you could directly compare this to the progress that your understanding of what happens in the mind of the toddler does. And I don't think that the things that happen in the mind of a college student are that much more interesting than those things that happen in the mind of a toddler. I think it's pretty much just a scaling and more knowledge and more experiences and so on. But the really interesting things happen much earlier. So I would look at them.
I kind of agree that if you're proceeding along the right path to AGI, or on a right path to AGI, then what your system does at the toddler stage is going to be pretty much the same as what it does at the college student stage. What I'm not sure about is whether there are various dead ends that bring you only to the toddler stage and are not extendable to the college student stage. Of course, I'm trying not to do that, even though I'm working on playing with blocks and toddler type stuff first. But as with your own work and Pei's work, it's using an architecture that had the longer term goal in mind, right? It's not clear whether there are dead ends that would get to the toddler level and no further. But yeah, going back to Josha's previous question earlier, I didn't want to reject the idea of finding some simple kind of self-organizing system that will somehow give rise to human-level AGI when exposed to the right environment. I think that eventually could be made to work. And I thought about that a lot before I started on the path I'm at now, because of coming out of the whole discipline of complex systems and self-organizing systems and nonlinear dynamics and so forth. The reason I'm not doing that is because it's not that clear to me beyond the general idea. And I played around with that for a couple years and didn't get to work and gave up, and so have many other people. But I haven't gotten OpenCog to be human-level AI yet either, right? So it's more, for me, a matter of, correctly or incorrectly, I have a clear mental vision of how to get from here to human-level AGI using the OpenCog path. I see in my mind's eye how all the parts will fall into place, and I think I see how it will all work. I don't think we're 90% there, as he joked, but I think we're tens of percents along the way there, anyway, in terms of architecting and teaching the system. Whereas for the other approach you mentioned, while it does seem feasible in principle, for me to work on that, I'm like going back to the very beginning. Like, I don't think it's a recurrent neural network at all. I'm not quite sure what kind of self-organizing infrastructure I'd want to use. I want to go back to some kind of artificial chemistry or something, and it all becomes pure research. So I tend to think that way is further off, but I think ultimately we'll have many, many kinds of AGIs built by many, many kinds of methods. But I guess my personal guess would be that AGI by brain emulation will come about before some kind of non-brain-based self-organizing pool of entities being nudged to form general intelligence. Because I think for brain emulation, all we need is brain scanning to work well. If we had brain scanning in vivo with high spatial and temporal resolution, then within some relatively small number of years after that, we would understand what's the dynamics in the brain, and we could build a virtual brain, which would not be the best AGI by any means, but it would be a start. Now that's probably decades away, because the rate of progress of brain scanning, while exponentially progressing, is not that incredibly fast.
Brain scan is probably decades away. Understanding how it works from that is probably centuries away.
See, I doubt it. I bet it's 5 years. Once you have the movie of what's happening inside each person's brain as they're thinking, that's...
Well, the little evidence we have of that, which is the 406 brain cells in the brain of this little worm that they have actually mapped, hasn't taught them anything about why it does what it does.
Well, but we don't have... what kind of data do we have from that?
It's a perfect map of all the neurons in this brain.
Yeah, but do we have single-cell recordings over time of all the activation flowing through them? We don't.
No,
we just have the layout.
No,
that's very different.
But if it's only 400, shouldn't you be able to derive that?
No, of course not.
Well, shouldn't it only be 5 years? But it's already been 5 years.
We don't have the data. We do not have high space and time resolution data for the brain of that organism. We have only the layout of the circuitry.
Uh-huh.
That's quite different.
So you think for billions of cells, that kind of data would help you, whereas, for a 400...
We don't have that data for the 400
No, I'm
cell
saying,
organism either.
no, we don't, but for a 400 cell system, you wouldn't imagine that should...
I don't think static connectivity data is going to be good enough for any organism. I think what you need is a movie of the flow of chemical and electrical activity through the system over time. And once you have that, then you have an inverse problem, right? I mean, you have the structure and you have the dynamics, and then you have to understand what's happening in the system. But just if you had a complete theory of the dynamics of the system, plus a static snapshot, then of course that would tell you we need to know. But the problem is we don't have a theory of the dynamics of the system. So having the static snapshot of the brain of the nematode worm doesn't really help because we don't know how to predict the next time from the previous time.
Nevertheless, those scientists thought that if we had a full map of those 400 neurons, and it took decades to actually do it,
I know many of the people...
We would know exactly...
I know many of the people working on that now, and they don't think what you just said.
No, I'm saying
maybe 20 years ago.
Before they had it. So, it's easy to make these predictions before you have the data. That if you had it, we could do X, Y, Z.
Well, I think, if you talk to those guys in private about what they really thought, I'm not sure what they would have said. Like the Human Genome Project is an example. Sure, the biologists told the US government, if we just sequence the human genome, then we'll have the cure to all diseases. But how many of them really thought that, or did they just want money to sequence the genome?
I'd like to do a little test of the longtime AGI people in here. If you were talking about the machine learning people only looking at learning and saying, okay, architecture doesn't matter, and some of the architecture people saying, okay, we have an architecture, now all we have to do is make it learn. And I completely agree. We have to look at both of those things. Those are both necessary components. Now, maybe I'll start with Josh over here. Could you go through the two sides of, okay, we have the challenge of building an AGI. What, in your mind, is the list of functionalities that we should look at the same time to try to impart to such a system? And what would be the engineering or scientific methodological principles for allowing us to achieve that engineering? And try to keep it below 4 minutes, because I want to pay Eric in that as well.
That's pretty mean.
I know. I will, and we will forgive you completely if you miss a couple of things.
Thank you. Okay, thank you. That's very generous. Basically, I think that we just only need 4 things. We need pretty universal representations that can capture the full breadth of the interesting aspects of the mental environment that we as humans live in. That is, we want to be able to have sensory data of all kinds, perceptual data, imaginations, language, and so on in a single representational paradigm. Then we need all the operations over these data, which include planning, learning, retrieval, memory formation, whatever you need there. Then we probably want to look at motivation and a system that motivates itself, that finds goals autonomously. And then we probably want to have modulation to adapt it to given environments, so we get into affective states. And we want to put this into the right kind of architecture, these 4 aspects of the system. So we have to find, this is a technical challenge, a framework that allows us to do this and do incremental research on a common foundation. So people do not just do one module and another one does another module, but there's no way to recombine the 2 of them. That's basically it. And
do you think current computer science framework for software development and programming and so on is sufficient to get to that point?
No, I do think that computer science is still in its infancy in many ways. I do think that the programming languages that we have are very restrictive paradigms that force us to do stuff manually in crazy ways and to think in unnatural ways and to express things explicitly that could be captured by machines theoretically in some kind of near future. And I think that just to get some idea how this is going to progress, if we think back to the beginnings of programming when people were still punching cards, I think this is this is in a way what we are at compared to what programming languages should be like. And when you did assembler, you already had a very big advantage over punching cards. But we are not there yet, and I do think that better programming languages and better software engineering methodologies will indeed help us a lot of doing things.
Do you have any thoughts on how they would be better?
When it comes to even a moderate amount of parallelism, we fail abysmally. And we need technical systems to act as a prosthesis there. And we need software development methodologies to fill in those gaps which our minds cannot comprehend well. And I don't think that we have even really started yet to get there. But it's just, I think, a tiny aspect of those things which might be missing for us to make much quicker progress. So I don't think that AI is much to blame for doing all the things that it did in not succeeding in producing artificial general intelligence in the past 60 years, because I think the whole science is still in its infancy compared to what it should be. And it's very understandable that first we reap the low-hanging fruits, we make some seemingly big progress in planning systems and natural language understanding and basic computer linguistics, but then the really interesting things don't happen for a very, very long time because we have almost exhausted the space of things that we can do with the current methodologies. I don't think that hardware is the problem. Of course, we will get better hardware and it will help a lot, but right now, for all of the architectures that we have in our very small community, I don't think that we ever run into a big problem which we cannot solve because our computers are too slow.
Hey?
Yeah, given this context, I guess I'm going to just stress what makes my approach different from other people's, rather than repeat a lot of things we all agree. I think the number one issue...
If you agree strongly with some of the things that have been said, that would be... I wouldn't mind hearing that.
Yeah. Again, I would rather go back to the very beginning, that is, what's the research goal? Actually, I have been, as Ben have mentioned, we have argued more than 10 years on many issues. Later and later, I more and more realize that...
14 years of arguing.
Yeah, 14 years.
And we still don't agree.
Yeah, it will never happen.
Is that a threat or a problem?
It's a state of a fact, yeah, if there's such a thing as a fact. I guess more and more, besides background, personality, that kind of thing, they all matters. I guess we are not exactly working on the same problem. We are working on a highly related problem, as I mentioned. It's my early lecture here. I don't think people, even in the AGI circle, are working on the same problem. Ben put much more stress on the capability about the problem. His definition about AGI system can solve complex problem in complex context, which I understand. On the other hand, my focus or stress is on I'm looking for the underlying principle. And especially I put a much stronger stress on the constraint under which the system must work. That is insufficient knowledge and resourcing. So actually speaking, we are working on highly correlated problem, but not the same problem. So according to Minsky's definition, I'm a typical example of physics envy. But to me, that's actually why I think that's what science is all about, is to find a simple principle behind a complicated phenomena. I know that intelligence is so complicated, there is no way for you to find something, can be explained, can explain everything. That's, of course, will not happen not only here, but in any branch of science. But still, I'm more interested to find something which is relatively simple and also can explain a lot compared to the other models in the same field. So that, I guess, will explain a lot of difference between me and Ben in the engineering disciplines.
We don't even agree on why we disagree.
Yeah. But anyway, that's from my point of view.
That wasn't really my question. Actually, that could be classified as the methodological part of my question. But my question also included, what are the functionalities that you would like that are necessary
Like you already
and
follow
possibly
all that.
sufficient in the system to get to AGI.
Yeah, I know. But to me, that directly follow from this.
Okay.
For example, when we see, all of us are kind of like somewhere in the middle in our approach, in our research. But when we see a function which is not covered by the current design, then we'll tend to build another model using some technology which is the current best for that function and try to adjust the other part of his existing design to make them work together. I almost never do that kind of thing. I would rather go back to the NARS design and say that if there's anything I can do within the current model to have that functionality, even if not 100%, if just 70%, I would rather do that rather than plug in another different technology which may give me 90%, because I'm more worried about, say, consistency, compatibility, which Ben already addressed. So that's because of that. That will lead to the more kind of methodological approach. So because of that, I think, according to my point of view, I see the major issue is, I fully agree with you, it's not in hardware. It's not even in software. To me, it's always in theory. We don't have a good theory about what intelligence is. Okay? Without a good theory, I don't think you can even start a meaningful engineering practice. Okay? So that's what I've been doing. But at the same time, I know that in this field, if whatever theory you have, they must be able to be implemented in a computer system. Well, otherwise, it doesn't count at all. So what I have been looking after is just a principle, unified principle, which can be implemented, which can also explain a lot, if not all.
What's in that
of the
set?
function.
A lot. Can you enumerate some of the key?
Yes, the key is adaptation and learning. Yeah, I want to design a system.
What scope? Could you explain adaptation to what? In what way? Under what,
Yeah,
what
adaptation
specific-
under the constraint of available knowledge and resource, with respect to some given task the system have to carry out.
And the sky's the limit.
Yes.
Okay.
Yeah, under that assumption, so you see that I never start. Well, even though later my system will say that we need to do reasoning, we need to do learning, I don't start from those as requirements. I start from a principle. I hope all those things will be naturally derived. For example, self-organization, constructionist, I believe all of those, creativity, discovery, but to me, they're not, you have a list of requirements, then you do something to satisfy them. They should directly follow from your principle if you get the principle right. So to me, I would rather sacrifice capability for the elegance of a theory, even though some people say, oh, that's not the right way to do. But to me, well, maybe that's clearly my bias, but that's the approach I have been taking.
And listening to you, I'm just so surprised by the fact that you're one of the few people that I seem to agree with on almost every aspect. And then it turns out that my witch hunt for the past decade has been basically people who have a hammer and therefore everything looks like a nail to them, and that would essentially be how I would describe you. So it's a surprise that I can have that belief and still agree at so many points. But that's for another discussion. Thank you. Eric.
Well, first, I don't think that I share any requirements with everybody in the so-called AGI community, except probably with space. For example, human intelligence is none of my concern. Human level intelligence is none either. My main requirement is, in the lack of theory of mind, we just cannot wait, and my main requirement is to build a machine correctly bootstrapped to help me build a better machine. To do what? To to act as an adaptive developmental control system. The goal is to control and pervade the organs of a plant, of a factory, not Nasimo stuff. I'm not interested in that. So, given this requirement and following requirement-driven engineering, all the capabilities, of course, there are just side effects, or more accurately, results of an induction process during the engineering. And again, in a similar fashion that they did just explain, I'm looking not for components, but for principles. Those principles, in our case, are 1, regularity, uniformity of knowledge representation. Principle number 2, the knowledge must be executable, because that's what constitutes the system. And if we want the system to grow and expand via the acquisition of knowledge, the result of learning should be amenable to execution and fusion in the existing code base. Third, it must be uniform also, because if the system is meant to expand itself autonomously, it must have a consistent executable representation of itself. In other words, the representation should be recursive and compressible. So this rules out from the onset, on a theoretical base, any sort of wiring and componentry, actually.